Welcome. In the last three sessions, we looked at examples of graphing explicitly given functions using calculus. While these are useful in certain situations, there are three problems with that. One is that it's a lot of calculation. It's easy to make simple algebra mistakes, which completely throw us off. Second is that it's also not very realistic. Very often we get information about the first and second derivatives not by calculating them, but based on something else. And finally, they also don't make very good test problems because we can just graph using a graphing calculator, substituting brute force for intelligence. So on the test, I'm going to give you problems like this example, where you have information about critical points, point of inflection, and the sign charts laid out for you. You just have to combine that into the graph. So you basically have to know the principles and how to apply them. If you are given values of the function that gives you points on the graph, information about first and second derivative can also be translated into graphical properties using the facts we have already seen. So this is a simple example to illustrate that. So let's look at the information. First three pieces of information are values of the function. So they tell me points on the graph. This is -3, -4, 0, 0, 2, 3. This tells me that f prime of 0 is 0. In other words, 0 is a critical value, horizontal tangent. It said that f is not differentiable at -3 and 2. So those are also critical values. The function might have either a vertical tangent or a cusp or a corner at those. We don't know which one it is. When we draw the graph, we might be able to narrow it down further. Finally, it says f double prime of 0 is 0, which means 0 is a potential point of inflection. The next four statements tell us something about the signs of f prime and f double prime. We will come to that at the end. Let's first plot the critical points. We know that there is one at 0, 0, which is just because f prime of 0 is 0 and f of 0 is 0. There's also a critical point when x is -3 and the point is -3, -4. Let's plot that as well. And it also says f is not differentiable at 2, so there's a critical point with x coordinate 2. The y coordinate is f of 2, which is 3. So the point is 2, 3. There is a potential point of inflection because we know that f double prime is 0 when x is 0. We've already plotted that. What is left is the sign chart information. Take the intervals into which the critical values and the x-coordinates of points of inflection divide the real line into. There would be -infinity to the first critical value is -3, then -3 to 0, 0 to 2, and 2 is the rightmost critical value, so nothing else of interest happens to the right of 2. So our intervals are -infinity to -3, -3 to 0, 0 to 2, and 2 to infinity. I'm now going to translate the remaining information into this sign chart. It says f prime is positive from -3 to 0, that is this interval. It's also positive from 0 to 2, the third interval. F prime is negative from -infinity to -3 and from 2 to infinity. F double prime is positive from 0 to 2 and 2 to infinity, negative in the remaining two intervals. So now let's translate the information from the sign chart to shape of the graph. In the first interval, -infinity to -3, f prime and f double prime are both negative, so the function is decreasing and concave down. From -3 to 0, function is increasing and concave down, because f prime is positive, f double prime is negative. At 0, there is a horizontal tangent, so the graph should become almost flat. From 0 to 2, the function is increasing and concave up. And finally, from 2 to infinity, the function is decreasing, concave up. Since there is no information about x-intercepts, we won't worry about whether there are x-intercepts or not. So now I have a graph that reflects all the given information. And this concludes our example.